So if we haven't traveled to the interior of Earth and we can't send a probe or anything down there, how do we know what's going on? How do we know that there is a liquid part of our core? How do we know that the mantle is molten? How do we know what it's made of? All of that. And the answer is seismic waves or seismology. This is all about earthquakes. When an earthquake occurs, there are a couple of different kinds of waves that can be measured. There are longitudinal waves, which is when displacement is parallel to the direction of the wave. Or if you have a slinky and you shake it up and down, what does it do then? The other kind of wave is a transverse wave. This is when displacement is at a right angle. Or if you have a slinky and you shake it side to side, what does it do? So longitudinal waves are like sound waves. Transverse are like shaking at a towel, or in elementary school, if you ever played with the parachute in gym, or if you're at a football game and the crowd is doing the wave, those are all transverse waves. When they happen with earthquakes, we call them different names. P waves are primary, they come first, and these are the longitudinal, the push and pull, the back and forth that happen very quick. These travel faster than sound, and they can travel in both solids and liquids, but they move at different speeds depending on what they are traveling through. S waves are secondary waves, and these are the transverse, the side to side, the shaking out a towel. They move slower than P waves and slower than sound, and they only travel in solids. So S waves are slower, they come second, and they only travel in solids. Here is what each of them looks like again. So a P wave is the push and pull. It is faster, and it can go in both solids and liquids. An S wave, on the other hand, is an up and down. It is doing the wave, it is shaking a towel. This is slower and it only travels through solids. These are things that we can create and observe in a lab and see how they move. And they also happen with earthquakes. So P waves are longitudinal. When they move through the ground and come back out on the other side, they're going to make your house or whatever bounce up and down. And remember, these can go through both solids and liquids. Transverse waves are that shaking out, that side to side motion, so they will make your house or a building move side to side during an earthquake. These are slower, so they show up after the P waves, and they cannot travel through liquids. So the time difference probably isn't super noticeable when you're living through an earthquake, but if you look at it in slow motion, this up and down happens first, and then the side to side happens. These two waves act differently. But we know, one, they get bent as they pass through different materials. This is called refraction, and just waves traveling through different densities will bend as they go. But we can look at where do we see the waves when there is an earthquake. So if an earthquake happens right at this point, the P waves can be found all over Earth. Even if it's not felt, if there's not the Earth on the other side is also shaking, there are sensitive machines that can pick up those P waves. S waves we don't find on the opposite side of Earth when there's an earthquake. So both of them get bent by the different densities, which give us a clue about what the material is, what these layers are made of. But S waves get blocked. We call back here the shadow zone because the S waves are getting blocked by something in the center. S waves can't travel through liquids, so that's how we know that there is liquid at the center of the Earth, because the S waves can't travel through it. They can only travel through solid, so they get stopped. So if we compare where we see P and S waves, what angle they're coming in at, if they've been refracted, where there are none, we can figure out the densities of the different layers of the Earth. We can figure out where there must be liquid and solid and recognize that there's got to be a solid core. We can also use that to figure out where an earthquake happened. So if I am at earthquake station D and an earthquake happened somewhere else, I know that the average speed of P waves is 10 kilometers per second and S waves are 6 kilometers a second. So if I want to know how far away was the earthquake, well, it took 900 seconds for the P waves to get there. Distance equals speed times time. So 900 seconds times the speed of 10 kilometers per second tells me that this earthquake happened 9,000 kilometers away. How much longer later did it take for the S waves to arrive? Well, time is distance divided by speed. So now I know my distance is 9,000 kilometers, and I know that my speed for S waves is 6 kilometers per second. So 9,000 divided by 6 gives me 1,500 seconds. So the S waves occurred 1,500 seconds after the earthquake. It took P waves 900, so 1,500 minus 900 gives me 600 seconds after the P waves, the S waves showed up, or 10 minutes later. It's typically not that big of a difference in real life. Earthquakes that we can measure and feel the P and S waves, there's maybe a couple of seconds in between. But if you're far enough away, if you're at C or even X or Y, well, X and Y, you're in the shadow zone. You're going to get S waves. But if you're at C or B, you're far enough away from this earthquake that you won't feel it. Houses won't shake, but again, sensitive material, sensitive equipment can pick up those P and S waves and give us clues about the density and thus what material the mantle and core are made of, and prove that this core has to be at least partially liquid because there are no S waves on the other side where S waves can't travel through liquid. So it is thanks to earthquakes and seismic waves that we know we have an inner core that is solid and an outer core that is liquid.